So, good afternoon. I see a lot of quarters on this presentation, so this is a job done also together with several companies and experts in the field of petrochemistry. There's also my specialty, and steam cracking is my first love, but I've continued since then, so I work on many other things nowadays. Okay. So I will start with the sort of general introduction. And first of all, I want to start with this slide. So this is an article from a certain period, and it deals about emissions of coal, a lot of tons and so on. And they speak about temperature rise. Now I want you to guess from which year this is. Anybody? You guess?
1912.
1912. Yeah. So it's not new. Yeah. People were aware. Yeah. Even in 1912, you can see it with the blue line. Yeah. So we always keep on saying this is new and so on. Well, as scientists, we keep on reinventing wheels, and maybe also here. But it's clear that we have to do something. Yeah. Why steam cracking? Why petrochemicals? It's the biggest chemical process for producing plastics. So it produces ethylene, propylene, but also aromatics, butadiene, and so on. So it's the main workhorse of the petrochemical industry. It also results in 250 million tons of CO2, but that's even an underestimation because it doesn't account for scope 3 emissions. And I will discuss that a bit later. And you can use a large number of starting materials. Most popular are ethane and naphtha, but you can basically put also vacuum solid oils or plastic waste derived oils and so on, many other things in the steam cracker. Yeah. So these 250 million tons or more are basically the reason why we want to reduce this and why we want to come up with a better process. And the logical step, of course, we maximize efficiency, we try to avoid it, or we go for circularity. And I will discuss all these different aspects in this talk. The good thing about the steam cracker is in the end that approximately 90% of the emissions come from the furnace in a modern plant. So the base case on the left, this is A. Here you see a steam cracking furnace, in this case fed with propane. It's a real furnace from Dow, benchmarked, and so on. So what happens is you put propane in, high temperatures, you have a convection section on your left. Convection section here, preheat the feeds, go to about 650 degrees, you start cracking up to 850 degrees here, you cool very quickly. This is to avoid side reactions of the ethylene and propylene, and at the same time produce high pressure steam. So this is the base case that I will be studying and comparing with other types of cases. This is a new invention by Technip Energies. Here, they maximize the efficiency of this radiative part. So more heat is basically going to the coils. Typically rated efficiency around 40%, here they went to 55%. This of course means that you can't recover this heat here. So you need tricks to make this steam up and also to preheat sometimes your feed. So you have, in this case, 2 TMs. You can also do air preheat. With an air preheat, you can further improve the efficiency of this radiant box that basically provides the high temperature heat here. This can also have an effect on the overall efficiency, but also on your emissions. And these are all patented that are recently used. Then we go to something completely novel. Yeah. So I've been working now for almost a decade with a company which is called Coldbook. And Coldbook invented in the end the worst compressor ever. Yeah. It doesn't compress anything. Yeah. It just transforms all rotational energy into heat. And the advantage, of course, is that a compressor you can electrify. Not needed, but it's possible. And this is actually what's happening in this machine. And you say that's impossible. You will not use a rotational machine to crack hydrocarbons. Yes, it's possible. It's built. It's operated, and on a relatively large scale. So it's not impossible. How does it work? Well, you basically come in on the sides, high velocities. The center part, the rotor, is rotating 40,000 RPM, rotating very fast. And basically what it does, it's accelerated by this rotor, and then it hits the diffuser, but at a very low angle. So what happens is, all this velocity, all this energy is transformed into entropy loss and transformed into heat. Again, worst compressor ever. You don't have any pressure buildup in the steam cracker you want to have. And what they do with cold boot, they make this kind of donut design. So you see the funnel going in a donut shape from inlet to outlet. And they have in this case out in the top 2 inlets or 2 outlets, and so on. The good thing about this machine is that it actually results in some selectivity increases. So yield increases if you crack propane, for example. And you see a difference of 4%. And then you say 4%, that's small. In the steam cracking world, that's enormous. Yeah? Increasing the yield with 0.1 weight percent for a typical cracker results in at least €1 million extra profit. If you go 4 weight percent, this means 40 million euro or dollar. We have recently invented in Ghent, and it's now patented, so I can say it. We have one which goes to 15 weight percent. That's 150 million euro. Then we have some other cases, blue hydrogen cases. So just for comparison, because blue hydrogen is also heavily studied, but you can also take green hydrogen. I'm not a believer of green hydrogen just because of the economics, the cost is too high. Blue hydrogen, from an economic point of view, can make sense. 2 cases, the classical steam methane reformer, and then autothermal reactor that we use as benchmark. With the autothermal reformer, of course, you see it. We basically use this heat, and here we made the methane reformer that we have a bit of flue gas, so should result in a bit of more CO2 emissions just for simplicity and to have some difference. Okay, then we go to the grid, and we studied 4 different grids. So the Norwegian grid is like the ideal grid, almost completely green. Then you have the Belgian grid. I'm from Belgium, so quite nuclear. So with not too much CO2 emissions. Typically European grid, and then the Dutch grid. So the Dutch grid starts from a lot of natural gas, and thus results in a lot of CO2 emissions. So depending on which electricity you will use and in which country, this will make a huge difference. And this is also what I like about the talk this morning. Will we put these steam crackers in at the same place as where they are now? So what we do with an LCA, but an LCA is in the end a complex word to look at, for me, mass and energy balances and then do some post-processing. So what we did is, of course, we used our detailed simulator. So during my PhD, I invented a simulation tool for simulating steam cracking furnaces. But on the other hand, you have to simulate the whole separation rate investment and so on, and you use that for the energy and raw material balance. And of course, then you do the post-processing with eco-invent and all these data, then you come up with numbers. Okay. Then, of course, with any LCA, you have to decide to cradle to gate or cradle to grade. In this case, I did cradle to gate because it's just too difficult to do cradle to gate for anything related to prep chemistry. What will you be using to compare and we manufacture close to recycling and so on. So we have a whole bunch of cases. So the left top is the base case, which is a classical steam cracking furnace. So then we have these 2 novel low emission furnaces, and then we have the RDR, so the electrified steam cracker, and then we have also the other cases with hydrogen and so on. Of course, for me, it's always easier also to reason in scope emissions, scope 1, scope 2, and scope 3. So scope 1 is related to what happens inside the plant. Scope 2 is related to utilities, but then mostly electricity used in that plant. And then you have scope 3, which are in the end to the emissions related to transporting that feedstock into that chemical plant. And not surprisingly, typically scope 3 is the largest for a chemical crashing plant. Yeah. For a steam cracker, it looks like this. So the main CO2 emissions from the scope 1 point of view, they come from the furnace. You also have some other emissions which can come from burners. Then you have here from scope 2 from with electricity. Then we have scope 3 related to the heat supply. So some results. Yeah. So this is a lot of data. Yeah. But if you let's start with the hydrogen case. So if you have something in red, we export it, so it's a negative value. Yeah. So here we produce fuel gas, export it. We also produce some steam here, so it's also exported, it's negative value. Then we have some direct emissions, which is of course higher for the steam methane reformer case. We have the propane upstream, which is in the end the scope 3 emissions. You need a certain amount of feedstock to get a certain selectivity. And then utility boilers that we have and grid electricity. So this means that you end up with these values, 1.5, 1.7, and so on. And what you see is that we basically have the largest value for the electrified reactor. Yeah. So, but also the smallest value. And again, it's all crucial where you put these facilities. So if you put them in the Netherlands, then you actually are a lot worse to the current state of the art, to the base case, which is a 1.85. But if you put them in Norway, then of course you're a lot better. Yeah. If you look at, for example, at low emission type of furnace, can also help you already substantially. But again, there you can also have an effect of the location. If you look at the other cases, there's somewhere in between. Yeah. So let's try to understand it a bit better. And then we zoom in. So you see here the base case here. So also auxiliary heat direct emissions. And then you see the grid electricity is actually one of the main contributors. And this of course explains why the electrification can be a good thing, but also a bad thing. Yeah. And this is something what people basically underestimate. The RDR also has a very low footprint, but it also has a very low footprint for a different reason. It's the only technology which actually results in a selectivity improvement. So you get more. So this is now designed for 1 million ton of ethylene production. Because it has a higher selectivity to the desired products, of course you need less heat. This results in a drastic reduction of the scope 3 emissions. Of course, what does it mean? If you would go with an alternative feedstock, so this is what we are currently doing together with, among other school group, is that we will of course no longer use propane, but we will use plastic waste derived oils. So they have a scope 3 emission of 0. Then you can really see that we drastically reduce your footprint. So in the end, electricity grid is important. Electrifying can be a good thing, but also you have to work on your scope 3 emissions because they are basically the most important. So RDR, it works. Has been demonstrated this year. Selectivities have been confirmed, have been presented at the Ethylene Producers Conference. Low emission furnace is, I think, a very good step in between. You can transform a furnace in a relatively straightforward way and use your existing facilities. Blue hydrogen can also be an option, but of course, today there's quite some controversy to blue hydrogen, especially in Europe. So it's not advisable. Well, so this brings me to the end of my talk. So I hope you enjoyed it. Thank you.
I may have missed this, so pardon me if I misunderstood. Are you doing direct methane to hydrogen production with high temperature pyrolysis of carbon?
No.
And the second question, of course, is have you thought about doing that particular process, which of course gets you a solid and a gas?
Yes. So I'm working on that with the largest chemical company in the world. So indeed, it's a very interesting option. Of course, there are a lot of different technologies to do that.
And none of them are great.
I think I have selected at least the best one, I would say. And in this context, we're looking at electrothermal fluid as gas. Yeah. And that's something quite novel. But of course, the material that you have as catalyst or as conductor is challenging. But the key thing is all, if you look at economics, is to make a carbon that has value. Otherwise, it becomes very difficult. If you just use hydrogen, economically it's difficult. You need to have a carbon which has value.
Is that for any questions?
So the results that you showed, they are from open compressor for steam extraction of
Yeah, so to the RDR, rotor dynamic reactor, that's the cold book reactor. So we worked with that for 10 years. Started a small Finnish company, and now they have a large demo plant which is in Geem, which is in the Netherlands. And they recently showed this racing machine that it actually works because, well, a rotating reactor working at 900 degrees Celsius, that's something that nobody really believed that would work. Now you see also companies like Siemens, Technip Energies, and many others stepping into it, but it's one of the few ways to get actually higher yields. And the trick is, you really need very short resonance times. And with this machine, you can go to 20 milliseconds resonance times compared to 100 to 200 milliseconds, and that results in higher yields. Yeah. We have now invented in GANs, the machine which can go to 5 milliseconds. Yeah. Then you have 58%. Of course, that's the whole.
Same question again.